constant. Geometric, a little bit different. What's in common this time with geo? The ratio, which means not A2 minus A1, but A2 divided by A1, or A10 divided by A9, or A100 divided by A sub 99. The ratio is constant, which means to get from one term to the other, you always multiply a constant. But you could be multiplying by a constant bigger than 1, which will be growing the terms, or you could be multiplying by a constant that's smaller than 1, in between 0 and 1. And what would happen if you're multiplying by like something so close to 1, but not quite there, like 9/10? It's still going to go down. Might take a little while, but it's still going to go down. The magnitude of the terms will decrease. Okay, so yesterday we were talking about geoseries and how there's a common constant that you're multiplying every time. Maybe growing, maybe decreasing, but either way, common constant that's growing. We do have some formulas. And we saw the A sub n formula says to get from A1 to any A sub n term, which I used A sub 4 as an example, but to get from A1 to A4, or A1 to A10, or A1 to A100, you're going to have to be multiplying by r how many times? N minus 1. Why? In between my first finger and my fifth finger, how many jumps are there? How many spaces? 1, 2, 3, 4. Uh-oh. To get from my second finger to my fourth finger, aren't there 3 jumps? To get from my third finger to my fifth finger, aren't there 2 jumps? So whenever you are going from one term to another, and usually with geo we're going from the first term, because we're usually given where it begins. If I'm going to the 4th or the 10th or the 100th, I'm going to go 3 jumps of r, or 3 multiplications of r, so r cubed. Or if I'm going to the 10th, 9 jumps of r, or 9 repeated multiplications of r to the 9th, or to a 100th term, 99 jumps of r, or 99 repeated multiplications of r, or r to the 99th. Now, yesterday we did have an interesting example, and that interesting example, this one was kind of straightforward, but this one, why was this one interesting? We didn't know the first or the third or the fourth. All we knew was the second and the fifth, and they said go backwards. But in order to go backwards, didn't we have to know how this term got to that term? And so there were a few different ways. One way was to kind of be like a creative problem solver and be like, well, you know what? I know how these work. And to get from here to here is going to be times r, times r, times r. I can make my own little formula and say, oh, sweet. 3 times r cubed gets here. Even though they didn't give me the first term, I can't go the 4 jumps of r from the first, but I can go the 3 jumps of r from the second. So you could have made up your own little formula, just knowing the behavior of the sequence, and then solved. Or we saw there was a little bit less creative way, but still just as accurate way, where you could have said, hey, there's an nth term formula for this guy. I don't know him, but I know what the term equals. And I know that it will be r to the 2 minus 1 from the first term. And this guy would be r to the 5 minus 1 from the first term to get to the fifth. And I know what the fifth term is. And then we could have made a little system of equations with 2 unknowns. We don't know the first, we don't know the r. And we could go ahead and solve. What I got down to yesterday was I was being silly and I did 3 to the 4th power. I forgot that was 81. I think I just wrote 3, which is horribly illegal. So you needed to raise 3 to the 4th power and a sub 1 to the 4th power. You would have gotten 81 over 8 to the 4th. Sorry. And then I was about to divide by 3. That's how that one canceled out to be 1. But if I divide one side by 3, don't I have to divide this side by 3? So then I end up with 27 over here. I could have reduced these guys, 1 of those and 4 of those, to go ahead and give me the cubed. So then I didn't actually keep on simplifying, did I? Pulling over that 3, that would have been 1 and then 27. Then I could have done some cross multiplication, makes this just a little bit easier. The 3 is gone, this one's a 27. But help me out, cool kids. What's 27 times 64 cube rooted? Wait a minute, you know what's really cool? Isn't 27 a perfect cube? Isn't that 3 cubed? And isn't 64 4 cubed? So if I'm cube rooting to get to my first term, aren't I just going to end up with 3 times 4? And isn't 3 times 4? Now, would it have been nicer in this example to maybe just stick with that whole make your own formula dealio that said like, hey, guess what? Ta-da! Go backwards by, well, if I'm multiplying by a fourth, divide by a fourth or times 4. This one's simpler, but you had to be creative. This one said, okay, whatever, I have some formulas. Let me plug in. I have a system. Let me solve. Both of them got us to 12. 2 different techniques specifically for the types of problems where they don't give us the first and we have to kind of figure out what's going on when they throw us somewhere in the middle of a sequence. And this one wasn't even in the middle. Didn't they just give us the second one? Man, it was so close, and yet it just kind of threw things off. But we did not get to cover yesterday the S sub n formula. So the S sub n formula, the nth partial sum. The S sub n formula, the nth partial sum. Sum means adding, yeah? So the nth partial sum means, remember, to add up the n terms. So you're finding the terms of this sequence and doing plus, 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 plus. And doing plus, 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 plus. Now, guys, I know there's something in your calculator. I know there's a sigma. I know there's a summation, right? I know that. The problem is, didn't we talk about how this test has a calculator, non-calculator part? Okay. So, well, how could you do this without your calculator? What does this look like? Right? Doesn't that look like this? What's another way of solving this? Okay, so we could actually, instead of having to plug in 1 through 12, right? We could just plug into this formula. Now, if I'm a computer, if I have a computer, if I can program a computer or use a computer program, that's not hard, as long as you have that cool sigma, right? However, if we're trying to do this by hand, or if we're trying to understand that this is a geoseries, well, hold on. Guys, what is my first term? What would be the first term if I was to expand? Remember, this has been condensed. This is a huge sum. What would be the first term? Because I need it for my formula. 4? Why? Because 1 minus 1 takes away the power, right? 0 wants anything to the 0 power. And PEMDAS says do the exponent first, but who's still out here? 4. So 4 times 1 would be my first. Now, hold on. Let's just get a feel for this.
In order to have the sigma formula, the A was already there. So you can do the math, but you already know the A.
Nice. In this one, but only because it starts at the same place that it's supposed to start, and it has the exact same form of what it's supposed to have. In my mind, reason why I'm having you plug in is because in Calculus BC, there can be geoseries that are written in a sigma that don't perfectly follow that pattern. So what I think is safer for right now for you guys, even though probably you'll see the ones that are most basic and that are written exactly like they've shown you, I just want to give you guys a heads up that geoseries don't always look. Does that make sense? Okay, but thank you, Kyle. You're totally right. This one does perfectly match that sigma notation, the formula. And so in this one, we could actually be like, hey, it's 4. But hold on. Why is this a geoseries? Besides the fact that it looks exactly like that one, why is it geo? What would be the next term? You wouldn't plug in 1, you would plug in 2. And if you do plug in 2, that would be 4 times, what would be the power of 0.3? 0.3 to the, 2 minus 1 would be 1. And the next one would be 4 times 0.3 to the second. And then that would be, now, with decimals, it actually gets kind of weird and it gets kind of hard. We can even say where this ends. This ends at 0.3 raised to the what power? 11 because 12 minus 1, right? 11 because 12 minus 1. But hold on. Maybe some of you see it's times 0.3 times 0.3 times 0.3, but that's kind of awkward. What's another way of doing this, guys? What's 0.3 as a decimal? as a fraction? 3/10. So couldn't this be 4 plus, what would 4 times 3/10 be? 12/10 plus, what would it be times another 3/10? Wouldn't it be 36/100? Plus, okay, hold on, wait a minute though. Would anyone leave it as 12/10? No. So it'd be 4 plus, okay, what would that reduce to be? 6/5. What would this one reduce to be? 9/25. If we were to go one more, we could multiply by 3/10 again, which is a little bit nasty. But multiplying by 3/10 again to get this next term that's missing, wouldn't that be 108 over 1,000? Oh, I wrote 10,000. Lo siento. Shoop, shoop, shoop. What would that reduce to be? 11/125? I don't think 11 goes in. How many times does 125 go into 1,000? You guys love your calculators. Why are we all staring at me, waiting for you to reduce that fraction when you could be doing what? What's something really cool that you can do in your calculator to reduce a fraction? Or couldn't you just type in 108 divided by 1,000 and then hit math frac? Did we not know that cool trick? 27 over 250. What's the dilemma? Does this look like a geoseries? How could you see if it's a geoseries? Okay, so we could, because I'm trying to show you, I mean, if it matches up perfectly, you're like, oh, it's a geoseries. But if they were to give it to you like this, which is kind of more like what the book usually does, right? Do you see that it's a geoseries? You're like, I don't know. We could go ahead and take this guy over that guy, right? And try to check our ratios. So A2 over A1. I just want to warn you, what if it looks very, very different? Would you have been able to know that it's a geoseries? Because this is kind of a nasty one. 6/5 over 4. What would that end up being? 6/5 all over 4 would be 6 over 20, which would be 3 over 10. And then if we did A3 over A2, that would be 9 over 25 all over 6 over 5. Remember, when you divide by a fraction, what do? Multiply by the reciprocal. 5 over 6 equals, that'd be 1, that'd be 5, that'd be 2, that'd be 3, 3/10. Whoo! But was that a super obvious geoseries? No. So be careful in homework, even though some things do match up exactly like, ooh, well, as long as I have that memorized, I would see it. Or as long as I wrote it like that, I would see it. But they could give it to you in fractions, and it's not quite as easy unless it's written maybe in a non-reduced form, where it's like, oh, hey, times 10th times 10th times 10th times 3 times 3 times 3. Just be careful. Just be careful. If it looks funny, you can always do these ratios to see if it is geometric if you're ever skeptical. Because sometimes, especially in this chapter, they might give you an arithmetic, like once everything's put together. They might give you a geometric, or they might give you what they would call a neither. Not all sequences in series are arithmetic or geometric. There are others, and others, well, let's just say, you won't necessarily be memorizing all their names, even if they have a name. So some are arithmetic, some are geometric, and then some are just plain old neither. Jason, keep it away. All right, so as we move on, Oh no, where's our problem? That's really sad. Find the sum of the finite geometric series, or no, sequence. Let me go find him. I think he should be right here, number 56. Who is this guy? And why is he missing? 56 gives us, uh-oh. That does not look exactly like that formula that we just looked at, did it? No, it doesn't look disgusting. But what happens if it doesn't look exactly like the formula? Nasty picture, I know, but it gets the idea across. N equals 1 to 10 of 3 halves to the n minus 1. Does it look exactly like this guy? Maybe. Do I want you to plug this in your calculator and solve? Nope. I want you to find the sum of the finite geometric sequence using a sub n is equal to a sub 1 times 1 minus r to the n all over 1 minus r. Which I just realized we never actually ended up solving that last problem. Go team. We'll go back to it in a second. But for right now, let's focus on this guy. They're giving it to us in a way that's like, okay, I think it might be. Well, they told me it's geo, so I guess it's geo. What's my a sub 1? Some of you might have compared to the formula and realized there is an a1 in front. Or you could have just plugged in 1 and been like, oh, it's 3 halves to the 0, which is the same thing as 1. That would be my first term. Okay, so if I'm plugging in s sub 10, why am I putting a 10 there? 10 is the upper bound, right? 1 times 1 minus, who's my common ratio? What's going to be multiplied every time in this one?
3 halves divided by 1.
Just 3 halves, right? Raised to the 10th power, all over 1 minus 3 halves. I don't know why I just wrote 10. I apologize. Shoop, shoop, shoop. Is that the sum? Yes. Why are some of you guys a little bit scared?
3 halves raised to the 10th.
3 to the 10th power, that's 3 times 3 times 3 times. Okay. I probably wouldn't make you do this one by hand. Let's go ahead and plug and chug it to your calculator. I want you to do it 2 ways. I want you to do it one way by plugging in the S sub 10 formula, and one way practicing your sigma notation. And what should happen when you plug them both in? They should match, right? So go ahead and practice with the sigma, go ahead and practice with the formula, and they do end up actually being what we need them to be, which is the same thing. Does anybody else get very different answers?
Yes.
Why? Because you plugged in wrong. In your sigma notation in your calculator, the big parentheses has to hold in the entire argument. If you chose to put that on the outside of the parentheses, the sigma just dealt with this guy and not that guy. So try again. If you did not put the whole shabam in parentheses, insert other parentheses, get that x minus 1 in the power or inside the sigma. You don't want this outside the big calculator notation. You want it inside. And guys, how do you change a fraction to a decimal if it's like you're using that really cool fraction-y thing and you need to see how it matches up as a decimal? Math and then decimal. Really quickly, turn to your groups and make sure that you have showing on your screen 113.33 for both The formula and the sigma. Turn, quick, make sure. Bum, 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 bum. Double check. Everyone okay? With the sigma and with the formula? It's really, put it in kind of wrong.
Whoa.
If you're done, go ahead and try the next one. Oh, no. The next one says, here's the series. I've shown you all the terms. Try to write it in a sigma. What's 1/4? But dividing by 4, isn't that 8? Divide by 8 would be 4. 24 is not 4. 3/4. Well, hold on. 4/3, wouldn't that be bigger than 1, which would make this grow? It's not growing, it's shrinking, so it has to be less than 1. 3/4. Are you guys finally doing the ratio thing? 24 over 32. They're both divisible by 8, and you will get 3/4. 18 over 24, divisible by 6, 3/4, and then you could keep on going from there. So 3/4 is your common ratio.
What's the F2 one?
It's a great question. To fill in your sigma, you need to know not only where it starts. Oh, we could put 32 as our initial term, right? Looking at our formula, our yellow box for S sub n. Our R, we just figured out, is 3/4. We could choose or show n minus 1 as our power. That's just plugging into the yellow box saying, hey, we know the first term. We figured out our common ratio. Oh, we're using n's instead of i's. Maybe we should have used i's, but that's okay. But don't we need to know when to stop? How could we do that? Could we multiply 18 by 3/4 and that times 3/4 and that times 3/4 until we get there? Yeah, that's one way. That's one way. But what if there were like tons of jumps in between? Oh, that could be tedious. Other way. We could actually like set it up as a formula, an a sub n formula, being like, hey, I want to know who n is. Now, this way would be kind of complicated. It would be kind of messy. Does anybody know what 0.125 is as a fraction? 125 all over tens, hundredths, thousandths, all over 1,000 is? Yeah, it's 1/8. Oh, but it's 10 and 1/8, right? So if it's 10 and 1/8, then wouldn't that be 81 over 8? We could divide by 32. So we would have 3/4 times n minus 1. And then that'd be 81 all over 8 times 32. This is getting kind of nasty, though, huh?
Can't you reduce a little bit?
Well, 81, 3 goes in lots of times. 9 goes in. But 2 and 4 doesn't go in at all.
I was saying, when you, is 81 over 8 times 32 over 1.
So we could make this, what, this would be 4 times 8, and that's, well, we could be 256.
Wait a minute.
Some of you might be realizing that 81 is actually a power of 3. It's 3 to the 4th. So then that might make you wonder, okay, well, if I have 3/4, then is this 4 to the power of 4?
Yep.
The answer is yes. And that actually makes life a lot easier because, guys, the other way to get to n minus 1 would have been so nasty. You would have had to use ln's to both sides and bring it down, which is totally a math thing. Robbie, let's make sure that everything is nice and open. And there you go. Thanks, buddy. Who would n be if this is 3 to the power of 4 and 4 to the power of 4? 5? Because n minus 1 needs to we can actually kind of cross off our common bases. Isn't this the one-to-one property? We like one-to-one properties. If we make this match, which we technically could, because we could say, hey, they're both to the power of 4. One-to-one property lets us not use ln's and all that craziness and just say n minus 1 has to be 4, so n has to be 5. How close were we up here? This was a sub 1, a sub 2, a sub 3. If we had multiplied by 3/4, we would have ended up with, what would that have been? 54? 54 over 4, which would be 27 over 2 as our next term, as our a sub 4. And then if we had gone one more time, we would have gotten to a sub 5, which is our 81 over 8. So we were super close. It might have been easier just to jumpity-jump until we got there. But either way, now we can go ahead and plug in 5 as our upper bound. But that can take some work. Did you guys hear me just a second ago say, if we couldn't make these match one-to-one property, we would have had to use ln? Pop down the power and solve, solve, solve. Okay, so this ends us at the end of section 9.3 at the question, what if the top bound doesn't actually bound it at all? What happens if the top, well, not no bound, it's not 0. It's not DNE. Let's keep going, doesn't it? Do you guys remember from section 9.1? Something to do with an infinite sum that actually equaled a number? And something to do with repeating decimals? As you guys are writing this page of notes, I'm going to do a quick little insert page and then dual page it so you can still see this. I really just need you to probably skip 2 lines. But in section 9.1, they have to think about 0.3 plus 0.03 plus 0.003. They didn't ask us what the name was of this or if there was anything in common. They just asked us to deal with it. But my question to you is now, is this an arithmetic, is it a geometric, or is it a neither? What kind of series is this? An arithmetic, a geometric, or neither? It is geometric. Can you tell what you're multiplying every time? What would move the decimal every time? 1 over 10. Isn't r equal to 1/10? R equal to 1/10. Sam and I were having a discussion, you guys might have heard it, might not have, a second ago about, well, a few minutes ago, about when r is bigger than 1 or r is less than 1. If r is bigger than 1, like if r is a positive number bigger than 1, and it's multiplied, what's going to happen to all my terms? They're going to get bigger and bigger and bigger. And if you add bigger and bigger and bigger values, what's going to keep on happening to your sum? Bigger and bigger and bigger. But what if I'm multiplying by an r that's smaller than 1, a positive r smaller than 1? Like 9/10 or 4/5, 4/5, thirds. You're going to be adding, and so since you're adding, it's growing, but since you're, but you're adding smaller and smaller amounts? There's this thing called Zeno's paradox. Zeno's paradox, actually Zenon's paradox, Zeno's paradox, there's a few different ways of saying it. But I want you guys to imagine a foot is a certain amount, like 1 foot, 1 unit, 1 inch is a certain amount, 1 mile is a certain amount. I want you just to call this 1 unit, how far I am away from the podium, yeah? If a certain distance from an object by covering half the distance every time. If I take a step covering distance, and the length is 1 unit, how far have I gone right now? Half of the unit, right? Plus, how far have I gone right now? A half plus a half of a fourth, right? So I've gone, it's true. And then what if I now go another half? I'm a half, and then a half of a half, and then a half of a half of a half, which is an eighth. So I've gone 4/8, I've gone 6/8, and now 7/8, right? Now just think about the idea. What if I was to add another half of that, and then add another half of that, and then add another half of that? I never actually get there. Because how many steps can I take? Well, how many steps, theoretically, could you mathematically show? Infinitely many. Plus, 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 plus. But as I keep adding and adding and adding and adding and adding and adding and adding, what am I never getting beyond? I'm taking infinitely, theoretically, infinite many steps. And yet, all of those infinitely one unit, right? So what's going on here? How many terms get added? Infinitely many. So I could write this as n equals 1 to infinity of 0.3 times 1/10 to the n minus 1. But what does this infinite sum equal? 0.333333333333333 1/3. An infinite sum held within a finite number. Now, how does that change our S sub n formula? Because S sub n says, oh, no. I can only find the sum when I have finitely many terms. Thanks, bud. You would do a sub 1, 1 minus r to the n, all over 1 minus r. We could plug in and say, okay, well, hold on. We know the a sub 1. We have the r, that's 1/10 to the n, all over 1 minus 1/10. We could actually change this 0.3, since we're doing fractions now, to be 3/10. How do we get the sum to be a third formula? Well, okay, hold on. I can say this is 9/10, right? And 9/10 divided would be the same thing as 10/9 multiplied. Do you guys see what? I do. But wait a minute. It's like this didn't have any meaning. 1 minus r to the n didn't have any meaning. Why? There's a snazzy thing in higher maths that say, I can't plug in an infinity as an upper bound because an infinity is not a constant. But I can say, can we have the n, which is the stopping point, going towards approaching? Ooh, approaching the arrow approaching. We talked about that earlier this year. We can't plug in infinity. It's not a number. But we can say, let's have n go towards infinity. And as n goes towards infinity, we would have this formula's n go towards infinity. What we do to one side, we do to the other side. And here's my question. What happens to 1/10 as you go towards infinity? Get smaller and smaller and smaller and smaller, which means calculus allows us to say, hey, this is 0.1, 0.01, 0.001, 0.0001, and bigger, it's 0.000. I know where you're headed. And where are you headed? Calculus lets us make the jump of, let's think ahead and think of where you're going. And where you're going as I go to infinity and I raise you to higher and higher powers is 0. 1 minus 0. What's 1 times 1/3? Can you guys check out this formula over here? Does it look like a lot like a sub 1 times 1 minus r to the n all over 1 minus r? But what's missing? The minus r to the n, because when r is not only less than 1, but actually also greater than -1, all the fractions in between -1 and 1 are all going to make the magnitudes decrease. Whenever that's true, The limit as n goes to infinity of r to the n equals 0. Whenever we have r's in between -1 and 1, the limit as n goes to infinity of r to the n equals 0, like we saw with the 1/10 if you raise it to higher and higher and higher powers, which means my s sub n formula, if I'm taking the limit as n goes to infinity of s sub n, and if I take the limit as n goes to infinity of my a sub 1, 1 minus r to the n all over 1 minus r, what happens? That guy goes to 0 and I'm left with this. However, this formula, I'm actually going to take away the s sub n, because s sub n says nth partial sum. This is not a partial sum. This is an entire sum. I'm going to make it an actual s, and I'm going to write the limit as n goes to infinity of s sub n. This formula only works if the sum exists. If, like the example I just gave you with Zeno's paradox, or if with the 0.3 and the 0.33 and the 0.33333333, if it actually exists. And guys, do you see the does exist when up here? So this is only for r within -1 to 1. Can I use this formula if r is bigger than 1? No. Now I put absolute value of r because it's like, okay, r is bigger than 1 or r is less than or equal to -1. Bigger than or equal to 1 or less than or equal to -1. But long story short, the sum, the infinitely many terms added together, will always exist, will always equal this variation on our original formula with the r sub n going to 0, basically going away. But it only works when r is in between -1 to 1. We call this infinite sum converging. And you can talk to BC kids and be like, hey, figured out geoseries converge when r is between -1 to 1, and they'll be like, ooh, good job. We've done a lot more. But anyway, still, it's kind of cool because they just spent about a chapter and a half, and they're about to finish another chapter dealing with convergence and divergence of infinite series, and it's a bit more complicated than geo. But geo is one of their 9 tests. Anyway, that was fun. How much time do we have left? Not very much. So, we just did that. Never mind. Let's get rid of that page. I just talked about limit notation. We'll talk more about that in chapter 12, where we get into calculus more. So what's going on as far as homework helps? I don't know. What looks hard, guys? Everything. You guys can A2 over A1. You can figure out the common ratio. Calculator? That one kind of looks like this one looks weird. Yeah? Maybe let's talk about number 82. This one looks weird. Do you guys see how the lines are only over the 0.18? Yes. So it's 0.3 plus 0.18. Ooh, no. Wouldn't it be 0.018?
Yes.
What would the next term be? Wouldn't it be another 0.00018? Does this guy even really relate to those guys at all? No. So I would actually separate this to be 0.3 plus, and then have this be your series that you're looking at. Once I have this series, question, kiddos, what's my common ratio? I do zeros every time, right? So isn't r going to be 100th? So could I have for this guy, my A1 be 0.018 and my R be 1 over 100? And could I say that this is the same thing as 0.3 plus the infinite sum of 0.018 times 1 over 100 to the n minus 1? I want that 0.3 separate. Could I find this guy with the S sub n formula? Yeah, I could. Couldn't I do? Because, guys, isn't this one of those converging ones where it's going to get closer and closer and closer to a number? So I'd have a sub 1 all over 1 minus 1 over 100 plus 0.3 3. I think it's possible. I don't think it's super gorgeous, but this would be 99 over 100, which 1 over 99 over 100, wouldn't that be 100 over 99? And I think some of you guys might actually be able to do this without a calculator. Bye, cool kids. Homework due on Monday. We have examples of, I think, the easy ones and the hard ones. Have fun going to infinity. I know. If we had time, we would see it today. We're going to see it Monday instead. I know. Aye. Oh, the 100 and that will move it 2 decimal places. So 1.8 all over 99. Should be 3/10 plus 18 over 990.
I'm still see you later.
See ya.